Today, we're looking at photon beams. We're going to look at actual data. And we're going to say, when you send a beam of photons with a bunch of different energies through a material, what happens when the photons come out of that material? How many photons are absorbed inside the material? And what does the distribution of energy look like when the photons emerge from the material? This is a little bit different than my other videos in that it's going to focus more on the physical theory, but we'll use Python for a few handy things, like computing statistics about the photon beam before and after it enters the material. If you enjoy this video, like and subscribe. Join the Discord server as well. Lots of people in math, physics, engineering from all over the world helping each other with various things, especially with courses, now that of course everybody's entering courses as well. Check out my other videos too if you enjoy this one, and enjoy this one. So other than the typical NumPy and Matplotlib, we'll be doing a little bit of interpolation and a little bit of integrating. This video is a great intro to interpolation if you've never done interpolation of data before, and you'll see why it's useful. And we'll be using the science plots Matplotlib here, so that's everything up top. So we'll start with a little bit of theory. And this is the theory of photon beams. So imagine you have a bunch of photons traveling in sort of like a beam-like fashion and hitting an object, right? And so you can imagine that the photons have an energy E. Remember that the photon energy is hv, h being Planck's constant, v is the frequency. So photons have different energies. There's X-rays, there's microwaves, there's gamma rays, a whole span of different energies of photons, and different energies make different colors too. Of course, that's the visible light spectrum. So a beam of photons with energy E, they're all the same energy for now, is sent through a material. And the number of photons decreases. So you're sending them through a material, as you can see in this picture here. There's photons coming in, you have n of them. There's a material blocking, and then you have a decreased number. That's an exponential here, so it's decreasing the longer this distance is. It increases with x. So mu, which is a function of energy, is the attenuation coefficient. So this determines how many photons are absorbed in the material, right? Because you get photons absorbed in the material and some pass through. And so mu is a function of E. So if you have really high energy photons, probably most of them will pass through, right? But the lower energy you get, then they'll start getting absorbed in the material more. So mu is a function of the energy of the photons coming in. So that's important. And so it's just exponentially decreasing. It's a pretty simple formula for this. But in general, a beam of photons doesn't have a constant energy. You send a beam of photons and there's a distribution of energy. Some are higher, some are lower. There's a standard deviation to the energy as well. And so, you know, this number of photons that comes out is dependent on mu, which is a function of E. But the number going in also, you know, there's a distribution in energy. So we have to consider all these facts. And there's an easy way to sort of tabulate this. So first of all, I'm going to let capital N as a function of E. This is the number of photons in the beam with energy less than capital E. So you tell me an energy, 2 MeV. And I can tell you, okay, 10,000 or less than that. And you tell me an energy, 4 MeV, and I can tell you how many are less than that. That's what capital N does. So it's the number of photons in the beam with energy less than or equal to E. And the reason I define it this way is because if I said N was the number of photons with energy E, well, then you're saying there's a certain number of photons with an exact energy E, but if there's a distribution, then it will be infinitesimal, right? You won't have any photon with an exact energy E. It's sort of like a probability density function. So you define N of V like this as the number of photons with energy less than or equal to E. So the number of photons with energy E is dN. So it's like the number of photons with energy less than this E, the difference between that, and then a slightly higher N. And so that's dN. So it's an infinitesimal quantity. And that gives you how many photons are with that particular energy. So dN is equal to dN dE times dE, right? This is just a thing here. So really, if you define dN dE, you get your spectrum of photons. So, if you're familiar with statistics, N of E is similar to the cumulative distribution function, or the CDF of a function. It's always increasing because you're always getting more and more photons with energy less than, the higher you make the energy, this sort of increases. And dN dE is like the probability density function. So that's sort of how that works. And think carefully about what's going on there. The number of photons at a particular energy is always an infinitesimal because you're dealing with continuous distributions. So the fluence is defined as capital phi of E, so N of V divided by A. So the number of photons with energy less than E per unit area. And this is like sort of what you would deal with in an experiment. You'd have some unit area or something, and there'd be photons hitting it. And you would count, okay, in how many seconds, how many photons hit this area. So this capital phi of E is just an easier way of tabulating this. And so it tells us that d phi of E, the number of photons with energy E per unit area, it's similar to how dN is equal to this. So you just plug this in, it's d phi to E dE, and using this definition here, you get a quantity like this. So beams are measured using d phi, and d phi dE is like the spectral density of photons. It's like the probability density function of a continuous distribution. So suppose one's given d phi to E, and if you're working in an experiment, you'll probably be given d phi to E. We'll say, okay, this is our beam, this is the distribution of energies in the beam. It's given by d phi to E. So suppose you send that beam through some material with a particular attenuation coefficient that depends on energy. What does the density look like after the photons move through that beam? So you have an initial density or a distribution of energies. How does that distribution of energies look like after it passes through the beam? Well, this is really easy. This formula I have up here, this is for like photons of a given energy. So I start with this. So the number of photons at a given energy is dN, which is a function of x and E, right? So as I go through the material, there's less and less, and there's different amounts of photons at different energies. It's equal to dN of 0e, that's just what nx and n0 are, e to the minus mu ex. And then I just divide by dE, I get this quantity here, and I get my fluence, or my spectrum of energies, dependent on the initial spectrum times its exponential. So our spectrum, after moving through some material of length x, depends on the initial spectrum as such. You multiply by an exponential, and so for different E's, it's going to decrease in different ways, right? So maybe at high energies, it doesn't decrease as much, and at lower energies, it will decrease more, so the spectrum will kind of melt, and you get a sort of high-pass filter. So this is like the equivalent of a high-pass filter, essentially, is what's going on here. You're multiplying the spectrum by some constant here. So let's look at some actual data here, right? I have some energies. These are in MeV. I have some values of mu for a particular material. This is like measured in an experiment. Like there's different values of mu for different energies. And I also have a spectrum of our beam. So you'll see what I mean in a sec. So I can plot mu as a function of E for our material. And the points here are actual data points, and the dotted line is just connecting them. So you see that mu actually decreases as I get to higher energy. So when mu becomes smaller and smaller, it means that more and more photons are passed through the material. The way you can think this is if mu goes to 0, if mu is equal to 0, right, then the spectrum always remains the same. So all the photons are just going through. So as mu gets smaller and smaller, as it gets closer and closer to 0, less of the spectrum is affected. So the higher photons pass through easy, and then it's the lower energy ones that really get attenuated. So they're the ones that get stopped in the material, is the lower energy stuff. So I can plot that, and I get something that looks like this. And so this is a property of the material. It's independent of the beam. We could also look at the beam. And so suppose I have some initial beam spectrum that looks like this. So if I want to run this, so this is what my beam looks like. It's sort of like a spectrum. And so I have, a lot of photons sort of at 2 MeV, and it sort of decreases like this. And I don't have very many low energy photons. So this is our beam, and this is our property of our material. And so this is sort of like we know what mu of E is, and we know what the beam is. And we can use this formula here to see how the spectrum changes. And that's as simple as just multiplying this by mu E x. So we'll do this for a few different values of x. So here is x equals 5 centimeters, 20 centimeters, and 40 centimeters. And I'm just taking this data, which is an array, and I'm multiplying it by another array. So you can think of this as being like an array, a bunch of different values of mu's for different energies. This is also an array, a bunch of different values of these points for different energies. So I'm multiplying, element-wise, the values in the arrays. And I'm seeing how the spectrum changes. So that's pretty simple. And I can plot this. And you see that for different values of x, for different, lengths and going into the material, it gets attenuated in different ways. So at higher energies, the points are all pretty close. It doesn't get attenuated that much, right? You can see that most of the high energy photons are still going through the material as x increases. But what's really happening is the lower energy ones lose. So you could see like a point here really decreases, and these points are also decreasing. So these are getting attenuated a lot more. So the lower energy photons are really getting stopped by the material. And at the end of the material, sort of like when I'm coming out here and I look at the spectrum, it's sort of more the higher energy photons that remain, of course. So these are the photons that are actually remaining. Now, this is where I get into sort of the Python part where maybe you want to compute statistics about this beam. And this is where data analysis is important. And you can see that these are obviously different bin widths, right? These points aren't equally spaced in X. So it's really a pain to take an integral when you don't have these equal bins. So I recommend doing this as follows. It's very simple. You interpolate this curve to get a function where I can give any value of energy I want and it will return a spectrum value. That's what interpolation is of data. You draw a continuous curve where suddenly you can pick any energy and you get a point. And then you can manually compute or numerically compute the integrals using SciPy's quad function. So the expectation value of e to the n, so this is energy to the power of n. You might think that's sort of weird where n is an integer, but it's how you compute mean and standard deviation, is given like this. So en, you're just doing a weighted sum, right? This is the continuous version of a weighted sum of e to the n times dn of e. This is the number of photons at energy e divided by the total number of photons. So you have a weighted sum of the energies. And then that's related, of course, to the fluence here. You can see just like this. So then the mean is just, well, n equals 1. That gives you the mean. The standard deviation is the expectation value of e squared minus the expectation value of e squared. That's just a statistic. And as a matter of fact, there should be a square root here. So it's a good thing I caught that. That's the variance, but if you want the standard deviation, you take the square root of it like that. So that gives us the standard deviation. And of course, there's other statistical properties you can compute. It's really annoying with the data that we're given, though. And so we'll do a few things. We're going to start by interpolating. So I'm given everything that is like underscore data is actual data points. They're sort of discrete like this and they're spaced far apart. So I always name my variables sort of important for understanding the concepts of these videos. So what I do is I take my e data and my mu data. So notice the underscore data for actual data points, actual things you measure in a lab. And I'm creating something called mu underscore f. And I do this in my other videos too. Underscore f means it's a function. You give this function a value and it returns a number. I've done this with SymPy and other videos, and I'm doing this here. So what I do, if I look at this alone, I'm saying I want you to interpolate e data and mu data. I want you to look at these data points here, and I want you to create an interpolated curve here, right? So that I can give any value of e that I want, and you'll return a value. So that's this, and mu f is a function. So if I go mu f and say I want mu f at, well, let's look at it at like 2.1, right? We don't have that data point. So I can look at 2.1 and it returns a number, right? It returns a value here that will be sort of interpolated like this. This is the spectrum. Mu f is this quantity here. So it's interpolating this curve. So I look at it at 2.1 and it returns an actual value here, which is nice. And I can look at that for a bunch of different values. So I have my mu f and I also have the spectrum f. So I have an interpolation for this as well. So I give it a number and it returns a number and it's using cubic interpolation, right? So now I have these functions. So everything here, let me undo that for a sec. Just delete these cells. Everything here are functions. And then what I do is I'm going to make a bunch of different values of E, which is what I do here. I take 100 different values between sort of the min and the max energy that I'm given in the data. And I get values. So continuous is like continuous. It's not truly continuous. There are 100 data points, but it's very dense, right? So you have a lot of data. And I use the functions that I created using this interp1d function to get a bunch of data points. And I can plot them and I can look at the continuous extension, which is this green curve. And really there's 100 data points, but it's so dense that it basically is like this. I mean, I could use 1,000 data points too or whatever. It's as many as you want since we have that interpolation function. So it interpolates like this, right? And this is a good assumption because you assume that there's not going to be any jagged edges. I mean, maybe if there was a phase transition or something like that, you might see a sharp transition, but I think this is a safe assumption here to do a cubic smooth interpolation on this data. I can also look at the continuous extension of our spectrum, which is what I do here. I have some data points and I'm smoothly doing it like this. And you'll notice that the data points aren't separated evenly in x, that's fine. I can use my interpolated function to compute integrals. So I can use this to compute the value of e to the n, which is given by this formula here. So I have a little function here that does that. It takes an x, right? Because of course, the spectrum depends on x. The further I go in, the more the spectrum changes. It also depends on n. Well, n is like e bar to the n. I'm taking the expectation value of e to the n, where n is just an integer. So I compute the numerator here. It's just it takes in a function. I'm using a lambda function, right? That's the first argument to SciPy quad. It takes in a function that depends on one parameter, and it returns e to the n, which is right here. D phi de naught, that's the initial spectrum, underscore f. So this is the interpolated function of a function of e. But this isn't quite equal to this. Remember, I have to multiply by the exponential as well, because this is the spectrum after attenuation has occurred, and this is just the initial spectrum. And by this formula right here, that's what I'm plugging in that integral. So I plug in that, and I multiply it times mu times x. And of course, this is a function of e. So I'm actually integrating over this curve, and I'm weighting it by e to the n. And I integrate from the minimum of the data to the maximum of the data. And I take 0. That's what quad, it returns the value of the integral and the error, so I'm only taking the value of the integral. I also look at the denominator, which is just this, only without the e to the n. So very simple. And it returns the fraction, which is the expectation value of e to the n. The standard deviation is just the expectation value of e squared. It's just this formula that I had up here. The square root of the e squared minus, e expectation all squared. Now I can get some data. I can look at the mean energies and the standard deviation of energies for different attenuation depths. So I'll change my depth of my material, and I want to see how does the spectrum of the photon energies change. And like I said, it's a high pass filter. It lets in more high energy photons. So you assume that the lower ones are going to be stopped in the material, and you have more high energy photons coming out. And you'll see that the mean will indeed increase, and the standard deviation does something interesting, right? The standard deviation is what's the spread of the energies in the photons like. So I can compute these means and the standard deviations. Takes a little bit to run. I'm vectorizing this function. I can't just plug in an array here, because quad depends on x. It's an argument here, and it can't take in an array like that. So I have to use np.vectorize to create a for loop over this function for all the different values of x for both the means and the standard deviations. All right, it's finished running. Now I can plot it here, and you can see that this is the mean of the energies. It almost looks linear, but it's not quite. And it says that the larger the material is, right, as I increase it more and more low energy photons get stopped in the material. The high energy ones keep going through, and of course the average energy of the ones that come out is going to be higher since the lower energy ones get stopped in the material. And again, that's because the attenuation coefficient is higher for smaller energies. So this is the mean of the energies like this, and it gets higher and higher, not quite linear. The standard deviation of the energies, however, it actually increases. At first you get more width in your distribution of energies, and then it decreases as you just get more and more higher energy photons and less lower energy photons. Anyways, I hope this was a cool introduction, a little bit different than my other videos. I hope it taught you something about photon beams and also how to deal with data in Python. Of course, all the data here is from data sheets where they only sort of give you discrete points, and we used interpolation to actually, compute things that we want to. Be sure to join the Discord server, like and subscribe. Check out all my other videos as well, and I'll see you next time.